All right, this is my explanation for these multiple choice questions. There are 13 of them. I just want to start off. This is probably going to be a long video. Um, and these are not easy. In addition to that, they were taken over 3 years worth of AP physics exams. So these were split. So there's 13 of them, and they were split between 3 years worth of AP physics exams. So there's 13. I actually didn't conclude all of them. I deleted some of the ones. There was probably 4 that I deleted because we've gone over it before. But at any rate, just to give you an idea, you might end up with 4 questions out of the 50, 4 or 5 questions on momentum. Okay. Number 1, a projectile is fired into the air and it explodes and it splits into 2 halves of equal mass that hit the ground at the same time. That's an important part. If the projectile had not exploded, it would have landed at point X, which is some distance r to the right of the launch point. After the explosion, however, one of the halves lands at point Y, which is a distance 2r to the right of the launch point. Where did the other half land? Here's my projectile. It takes off. I'm going to look at it as if it didn't explode. Here's where it would have landed, which is a distance r from its launch point. So this is a distance r. That is the center, and so here's the projectile. This is the center of mass. If it would not have exploded, center of mass, COM, center of mass. Okay, COM. That's a very common subscript. All right. However, it exploded. So here it is up in the air. It's split in half, and one of them landed at point Y, which was 2r from the launch point. So now it's a distance, additional r from X, where it would have landed. So if I have this half, which is half the mass located at point Y, where did the other half land? Well, the other half had to land back at the launch point. And here is its mass, because the center of mass had to be the same as it would have been if the explosion never occurred, because of the fact that conservation of momentum applies in an explosion as well as the collision. So the system's initial, so the momentum of the system initial has to equal the momentum of the system final, right? And so that is the mass of the system times the velocity of the system has to equal the initial, mass of the system times the velocity final of the system. That velocities between the initial and final are identical. So that center of mass velocity is the same. Now, wait a minute, Mrs. Crary, what if I exploded and it went upward or it went downward? Well, they gave you a piece of information that indicated that that explosion created a force only in the X direction. And here's why. It hit the ground at the same time. So that means the height had to be the same. Those points did not, or those projectile pieces had to go in the X direction, because if it went up and down, then they would not have hit the same time. So for example, let's assume that it broke up and a piece went that way and a piece went that way. That would not have hit the ground at the same time. So the answer is at the launch point. Number 2, graph above represents the position of 2 identical carts. Both of them have the same mass on a straight horizontal track as a function of time. Which of the following statements about the magnitude of the momentum of the 2 cart systems' center of mass is true? So I look at the answers generally, and I can see that we're talking about the momentum at these different time intervals, and something occurred at 2 seconds. So I'm going to look at the momentum of the system between 0, so the center of mass, so I'm going to calculate the momentum of the entire system between 0 and 2 seconds, okay, because things look pretty constant during that time frame. So I want 0 to 2 seconds. And I see that this is a position versus time curve. So for cart 1, its velocity before 2 seconds is equal to the slope of that line, which is 1 unit divided by 2 units. So it is a half. So that velocity is a half, or 0.5 meters per second. Okay. Cart 2 has the same slope, meters per second. So there's its velocity. And we were told that the carts were identical. So I'm going to just multiply times 1 kilogram. I don't care what the masses are, but they're identical. And so my momentums are both a half. So that's of the individual carts. So I'm going to add them together and find that the momentum of the system initial is equal to 1/2 plus 1/2 is 1 kilogram meter per second. Okay. And that's the momentum of the center of mass of the system, right? Okay. How about after, between 2 to 5 seconds? So between 2 to 5 seconds. Well, cart 1 has a velocity. So I'm going to look at this slope of 2 over 3. Mass is 1, right? Cart 2 has a velocity of 0, and mass was 1. So the momentum of the system final is equal to 2/3 times 1, so 2/3 kilogram meters per second. All right, now let's go look. The momentum of the system center of mass is constant between 0 and 5. Well, I just proved that it's not. I have a momentum in between 0 and 2 of 1 and a momentum between 2 and 5 of 2/3. So that is no. Momentum of the center of mass, which is of the system, is smaller after 2 seconds than it was before. And that is true because 2/3 is less than 1. So B is the answer. C is not correct because it is not larger. And then the system's momentum increased at a constant rate from 0 to 5 seconds. No, from 0 to 5 seconds, there was a change, and the velocity wasn't even constant. So anyway, D is wrong. Okay. All right, number 3. Sphere 1 of mass m and sphere 2 of mass 2m hang from a light string. Sphere 1 is pulled back as shown above and released from rest. Okay, so I have a couple pieces of information here. Sphere 1 has a kinetic energy, Ki, immediately before colliding with sphere 2. The two spheres stick together and move horizontally for an instant, right? They both have a horizontal and then they're going to go up. So at the nanosecond after they hit, they're going to have that velocity for a nanosecond that's horizontal before they start to swing up. And during the collision, they want to know the change in kinetic energy of the two-sphere system. Change in kinetic energy, I'll use K just to keep it simple. Whoops. So change in K equals K final minus K initial. Notice all my answers are in terms of kinetic energy initial. And this is tricky. So we've got to figure out how to get that K final in terms of K initial. All right, well, let's see. Kinetic energy initial of the system. Okay, so here is block M with some initial velocity right before it hits the 2m sphere. So K initial is equal to 1/2 the mass of block M times its initial velocity squared. Well, it just so happens that the kinetic energy initial of the 2m block is 0. So we don't have to take we can ignore that because it was at rest. Well, what is kinetic energy final? Well, kinetic energy final, I need to know the final velocity of the two spheres. So I've got to use my conservation of momentum to find it. So momentum initial, which was V initial times M plus 0, so that's the initial momentum, is equal to, what's the total mass after the collision? 3m times V final. V final is equal to a third of V initial. I need to get that final velocity into terms of V initial because I got to get kinetic energy final in terms of the initial kinetic energy. So that is my final velocity of my two sphere system after they stuck. So my kinetic energy final is equal to 1/2 the total mass, which is 2 plus 1. So I have 3m times V final squared. V final squared. So I have to square this entire term. So what is V final squared? That is equal to 1/9. 1/3 squared is 1/9 times V initial squared. Now, I'm going to pull out of this my kinetic energy initial, 1/2 m V initial squared. I'm going to group those together. 1/2 m V initial squared. So there it is. And what am I left with? I'm left with 3/9, which is 1/3. So the kinetic energy final is 1/3 that of the kinetic energy initial. Back to the question. What are we looking for? The change in kinetic energy. So change in kinetic energy is equal to its final kinetic energy, which is 1/3 Ki, minus its initial kinetic energy, which is what we called Ki. So 1/3 minus 1 is equal to -2/3 Ki. And here is my answer. It is not an easy problem. Practice it, okay? The answers gave you an indication that you need to get your kinetic energy in terms of the initial kinetic energy. So you had to kind of do some algebra. Number 4, I have a 12 kilogram block with the velocity of 4 meters per second. Velocity initial, let's see if I can talk and type at this, or right, 4 meters per second. It travels over some distance 4 meters for some time 2 seconds, and I have obviously some final velocity. I don't know what that final velocity is yet. They give me some information about the coefficient of friction between the block and the floor since it's sliding, that is the mu k. I may or may not need it. Sometimes they give you more than you need. The magnitude of the change in momentum of the box during this time is most nearly change in momentum, momentum final equal minus momentum initial equals question mark. In order to find this value, I need the final velocity. I don't know the final velocity, but I can find it. I have two different ways. 5, 4, 3, 2, 1. I have 1, 2, oops, wrong one, 3 variables. So I should be able to find the final velocity, okay? That's actually the quickest way. It is the equation that you must memorize that's the easiest. V final plus V initial over 2, that's your average velocity, times time. I can solve for final velocity, which is equal to 2 times delta x divided by time minus V initial. 2 times delta x, 2 times 4 is 8, divided by 2 is 4, minus the initial velocity, which was 4, and V final is equal to 0. So that's an easy way to quickly find the final velocity. There is another way. Work done by force of friction is equal to change in kinetic energy. Work done by friction is always negative, so negative times the force of friction times the distance is equal to the kinetic energy final, which is where the final velocity is located, kinetic energy initial. You had everything you needed to be able to calculate that. If you found the final velocity using this work energy equation, you will find that to be 0. I have done it but the kinematic equation is easier in my opinion, but it depends on how your brain works. Once again, back to the question, what's the change in momentum? I have my final velocity now, so my final momentum, which is 0, minus the initial momentum, which is the mass, times the velocity, which is negative 48 kilograms meters per second. They wanted the magnitude, so the negative goes away. The answer is B. Number 5, if you know your stuff, you don't even have to calculate anything. Some of these are super long. Some of these require no calculations. We have trial 1 of an experiment. We have a cart that moves with an initial velocity on a frictionless horizontal track and collides elastically with another cart that is initially at rest. That collision momentum is conserved, kinetic energy is conserved. In trial 2, the setup is identical, except they stick together and during the collision. Momentum is conserved, kinetic energy is not. How does the speed of their center of mass change, if at all, during the collision in each trial? When I have conservation of momentum, the momentum of the system initial must equal the momentum of the system final. Essentially, that velocity of the system initial, which is the velocity of the center of mass, is going to equal the velocity of the system final, which is the velocity of that center of mass, because the mass of the system certainly didn't change, because otherwise it wouldn't be closed. And anyway, so we know that it does not change. So answer is A. Okay, center of mass of the system, if momentum is conserved, its velocity remains the same the entire time. Number 6. We have 2 blocks on a horizontal frictionless track. Surface, block A is moving with an initial velocity of V0 toward block B, which is stationary as shown above. They collide, they stick together, they move off with some velocity. So here they are, A, B, with a velocity V0 over 3. So whatever the velocity is afterwards, it's to the right, it's a third the original velocity. Which block, if either, has a greater mass? Momentum is conserved, that deals with mass. Let's use that principle. Initial momentum, mass of A times V0. That's the initial momentum of the system because the momentum of B is 0. The final momentum is the mass of A plus mass of B, total mass, times the velocity, which they told us was V0 over 3. So let's solve. Let's guess what cancels. V0. I can divide V0 from both sides. Okay. Now I'm going to rearrange that equation. I get 3 times the mass of A equals mass of A plus mass of B. I subtract mass of A from both sides. 1 times mass of A. So 3 minus 1 is 2. MA equals MB. Mass of B is twice the size of mass of A. Number 7. This is weird, and they will do this to you where you haven't seen something. This is acceleration versus time. Kind of looks, and here there's all these different questions here that has to do with collisions. Now, wait a minute, Ms. Query, we've dealt with force versus time. This has to do with the momentum impulse theorem. Force times time is equal to change in momentum. Well, what's inside that force? It's mass times acceleration times time equals delta P. Well, this is what's being graphed. This mass is being left out. Okay, it's constant. They told me that they have the same mass. So if I could create that force versus time by just taking every single one of those data points and multiplying it times some constant number. So it's no big deal, all right? Other than it looks weird. All right. They have the same mass but different bumpers. The acceleration of each car during the collision with a wall is measured and the data are shown in the graph above. Which of the following statements about the collision is correct? Okay. Well, force versus time curve, acceleration versus time curve. I assume that the mass is 1, then all of a sudden, hold on. All right, back to where I was after my interruption. If I assume the mass is 1, I multiply every single point by 1, and essentially that graph is a force versus time curve. So I'm going to use these areas to kind of figure out probably my change in momentum, I have a feeling. But anyway, okay, A, both reached their maximum speed at 10.5 seconds, which is this location here. Well, on first examination, you say, okay, well, it's maximum or the biggest change has occurred. Well, what's happening on this second part of the graph? I'm still accelerating. So I'm still accelerating in the negative direction. So I'm still increasing my speed in the negative direction. So I am actually going to reach my maximum speed at approximately 10.1. Okay, so this one's wrong. Okay. The cars experience approximately the same impulse. Oh, by the way, they want us to pick 2 answers. All right, impulse. Well, I got to calculate the area under the curve. If you calculate this area, which is 2 triangles, and you calculate this area, which is 2 triangles, you will find those areas to be the same. That is a correct answer. Car B experiences a non-zero force for a longer time than car A. Car B, here's the time frame in which I experienced a non-zero force, and they're claiming that it's longer than car A non-zero force, and that is false. So, no. At this point, you would have to assume D is correct, but we can figure that out. The change in momentum for car B occurs over a shorter period of time than that for car A. The change in momentum for car B, shorter period of time versus the car A, shorter period of time. That is correct as well. All right. Another tricky problem with regards to fractions and ratios. That's really kind of what it is, in my opinion. I have a block of mass M. It slides along a frictionless surface with some initial kinetic energy. I have some initial velocity. It collides with the block of 3m. Its velocity is 0. Its kinetic energy is 0. They stick together. I have 4m with some velocity final. I need to know the ratio of the final kinetic energy to the kinetic energy initial. In order to determine that, I need to figure out what my velocity final is. Okay, so let's do some conservation of momentum. All right, let's see. The initial momentum is velocity initial of this M block plus 0 equals my final momentum is 4m times v final. So v final is equal to 1/4 v initial. Okay. All right. Kinetic energy initial. Kinetic energy initial is equal to 1/2 the mass of m times v initial squared plus 0 because of the 3m block had no kinetic energy initial. Kinetic energy final, 1/2 times the mass, which is 4m times this entire velocity value squared, which is 1/16. Let me find my notes so I don't get lost. Yep, 1/16 over v initial squared. I'm sorry, v initial squared. Okay. Now I'm going to pull out and group this. So I have kinetic final is equal to 1/2 m v initial squared. That's my kinetic energy initial times what's left over, 4/16, which is the value of 1/4. So kinetic energy final is equal to 1/4 the value of kinetic energy initial. So kinetic energy initial is got to be 4 times, I'm sorry, kinetic energy final is 1/4 the value, okay, of kinetic, it's smaller than kinetic energy initial. So now let's go look at what they wanted and what order they asked for it in. Kinetic energy final, the ratio of it to kinetic energy initial. Initial needs to be 4 times as big, okay? So final is the first value, so 1, and which one shows an initial kinetic energy that's 4 times as big? The answer is D, okay? Grouping, you got to group all those. All right, here's another one. They're going to do the exact same thing. A brother and sister are standing next to each other on a surface. The brother's mass is twice the mass of the sister. Her mass is M. The sister suddenly pushes her brother. As a result, the sister moves with some kinetic energy, K. So we'll call that the, I don't know, initial, or let's call that the V. I'm not sure what I called that. What did I call that on my paper? Hold on. Oh, I just called it V. Okay. What is the resulting kinetic energy of the brother? Okay. I have to find that velocity. I'll call that the final of the brother. I need to find his velocity in order to find his kinetic energy. So we got to use conservation of momentum. What was the initial momentum of the whole system? Everything was at rest. So initial momentum was 0. What's the final momentum? Well, the brother's moving to the left. So we have negative 2 times m, because it's twice the mass, times his final velocity. And why is it negative? Because it's moving to the left. What was the sister's momentum? It was her velocity times her mass. Final velocity, okay, 2mvf equals vm. The final velocity is equal to, of the brother, is equal to 1/2 times the original velocity of the, or the final velocity of the sister. Okay, now, again, what are we trying to find? We get lost sometimes. We're trying to find the kinetic energy of the brother. So kinetic energy of the brother is equal to 1/2 his mass, 2m, times his velocity squared, so that whole thing squared, which is v squared over 4. I'm going to pull out what was her kinetic energy. What was her kinetic energy? Her kinetic energy was equal to 1/2 mv squared. Okay, so let's go find the terms. There's the m, there's the v squared. So let's group those together. So I get, this again is the brother, 1/2 mv squared. So, and what am I left with? 2 over 4, 1/2. So his final kinetic energy is half of his sister's. Yep, not easy. Okay, this is the one that I really struggled with. Let's be real. Okay. I'll tell you how to do this. No, that's not true. There's another one. All right. A block of mass m travels with speed v naught to the right on a horizontal surface with negligible friction towards a sphere of mass 2m hanging at rest from a light cord as shown above. The block collides elastically with the sphere. Which of the following correctly describes the speed and direction of the block and the speed of the sphere a short time after the collision? Okay, so now elastically, momentum is conserved, kinetic energy is conserved. We don't know, it didn't tell us it stick together. In fact, they don't. We have to test each one of these answers to see if it, let's see, if it meets both conservation of energy and momentum. And I'm going to tell you, it's easier to test the momentum. And right away, I see that I have these weird ones down here where I have zeros, but just for chagrins, let's test them. Okay. So what was the initial momentum of the system? And so for every single one of these, the momentum initial of the system was v naught times m. The sphere had no momentum. So this is the initial momentum. So we're going to test These are the final velocities, and we're going to test the final momentum of the system, which is equal to the momentum. I'm testing D right now, of the block, which they said was V naught to the left. So it's negative V naught times the mass plus 0. Okay, and notice that does not equal the initial momentum of the system. It would if you're not paying attention to the negative. How about C? Does that meet the conservation of momentum? This is, by the way, final. Well, I have 0 plus, they said the velocity of the sphere was V naught, so it would be V naught times 2m. Well, 2m V naught does not equal this V naught m that we got originally. So this is no. Okay, how about B? The momentum final is equal to, well, they tell me V naught over 3. So I have m times V naught over 3 plus, then they tell me this mass. So I got to multiply or add 2m, which is the mass, times the velocity, which is 2V naught over 3. Okay, so I got to do some fractions. I've got 1/3 mv naught plus 4/3 equals 5/3 v naught m. Okay, so this one's no, because 5/3 v naught m does not equal v naught m. Let's try one more. A. Obviously, A better be right, correct? I did it in reversed order on purpose. Momentum of the system final. Momentum of the system final is equal to, well, V naught over 3 to the left. Okay, so what's the mass? And it's negative V naught over 3 plus, well, 2m times 2V naught over 3. So I have a negative 1/3 plus a positive 4/3. 4 minus 1 is 3 over 3, which gives me V naught m. A is correct. Now, I've already proven that B, C, and D are not possible. But you can take this and then confirm that the kinetic energy initial, which would have been the mass times V naught squared, and then you could have calculated kinetic energy final. And it's ugly because there's lots of fractions, but I have done it. And for the sake of time, I'm not going to do it in this video, but it is the case. Testing, if you would have found that maybe A and B would have been correct and both had conservation of momentum, then you would have had to check the kinetic energy. But that's harder, so don't do that. Check the momentum first. Block A of, I'm on 11, I have 2 more to go. Block A of mass 2 kilograms is released from rest at the top of a 3.6 long plane at 30 degrees, as shown in the figure. After sliding on the horizontal surface, it hits and sticks to block B, which is at rest, has a mass of 3 kilograms. Assumed friction is negligible. The speed of the blocks after the collision is most nearly what? B equals question mark. First thing you need to do is use conservation of energy. You have to find this height. You use SOHCAHTOA to do it. That is the opposite side of 30 degrees. This is equal to 1.8 meters. Sine of 30 times 3.6 is equal to 1.8. Now I know that potential energy due to gravity has to equal this kinetic energy final. I get mgh initial equals 1/2 mv final squared. Mass cancels. V final is equal to the square root of 2gh initial. Plug all that in and you find the V final at the bottom of the incline is 6 meters per second. Now I have to use conservation of momentum to find the final velocity of A and B after they stuck together. The initial velocity of A is 6 meters per second times its mass, which is 2 kilograms, plus 0 because the momentum of B is 0. The final momentum of the two blocks together is their total mass. Their masses are 5 kilograms times V final. The final is 12 divided by 5, which is 2.4 meters per second. Personally, 11 is the easiest one we've done so far. Number 12 is one that I could not figure out. I had to actually ask someone, and within 5 minutes, he knew the answer, and that person is Mr. Sadowski. Okay, so do not feel bad if this is really difficult. Okay, two lab carts have the same mass. Okay, same mass. They are free to move on a horizontal track. The cart's wheels have negligible mass. Okay, fine. Cart 1 travels to the right at 1 meter per second and collides with cart 2, which is initially at rest, as shown at the left. Okay, so I have 1 meter per second up here, and this velocity of cart 2 is 0. Cart 2 has a compressed spring-loaded plunger with a non-negligible amount of stored energy. What kind of energy is that? Potential energy due to the spring. During the collision, the spring-loaded plunger pops out and stays in contact with the cart for 1 second, 0.1 second, as it decompresses. Here's something that I did notice this. In fact, it was me that told Mr. Sadowski this. Negligible mechanical energy dissipates during the collision. What does that mean? That means the kinetic energy from the collision was not lost. Okay. All right. Taking right as positive, the cart's velocity after the collision would be which of the following? Select two answers. All right, this is an energy problem. Essentially, what has happened is all the kinetic energy initial during the collision has to equal all the kinetic energy final, okay, plus the kinetic energy that we gained from the spring. I will say gained from spring, okay? Because we had potential energy due to the spring and we gained some energy from that release, okay? So what we can do is figure out the kinetic energy initial. What is the kinetic energy initial? Well, it's 1/2 times the mass of cart 1. They didn't tell us the mass. All right, they say the masses are the same though, right? Let's see. Yep, they have the same mass. So when they do that, just assume 1 kilogram. So mass of 1 kilogram, velocity initial was 1 meters per second. So here is the initial kinetic energy. I said it's a 1/2 joule, so 0.5 joules. All right. My total energy after I finish better be greater than 0.5 joules. I didn't lose any in the collision and I gained some from the spring. And so we will check each one of these options to determine if the final energy is greater. So kinetic final is equal to, well, 0 plus 1/2. We assumed the carts had 1 kilogram to make our lives easier, times 1. And that is equal to 1/2. That's not greater than 0.5. That is equal to 0.5 joules. So I need it to be larger. All right, let's try the next one. I have 1/2 times the mass, which we assumed was 1, times 0.5 squared, plus 1/2 times 1 times 0.5 squared. And that will equal, let me find my paper. .25 joules. No, this doesn't work because that's less than 1/2, so I lost energy. Kinetic energy final. We don't really know. So they told us, by the way, to select two answers. Kinetic energy final, 1/2 times the mass times 0.5 squared, plus 1/2 times the mass times 1.5 squared. And we will find that value to be 1.25, which happens to be greater than 0.5. That's an option. And kinetic final equals 1/2 times 1 times 1 squared plus 1/2 times 1 times 2 squared. and we'll find that to be equal to 2.5 joules. That's also greater than 0.5 joules. C and D. One more to go, and it's an easy one. A cart of mass m is moving with negligible friction along a track with known speed vi to the right. It collides and sticks with a cart of mass 4m moving with known speed v2 to the right. So we have v1 to the right, m. We have another one of 4m moving v2 to the right. They collide and they stick, and now we have 5m with some velocity, okay? Which of the following two principles, one or the other, conservation of momentum and conservation of mechanical energy, must be applied to determine the final speed of the carts and why? Hopefully you see that only conservation of momentum, because momentum lost by one car is gained by the other, and there is only one unknown quantity. Both conservation of mechanical energy, no. Okay. Both conservation of mechanical energy and conservation of momentum, no. Either conservation, no. All right. So that's what I've got. I know these are hard, but my suggestion is to take your time, watch the videos, and then rework them without help, and get practice doing what I consider some of the harder multiple choice problems. So that's what I got.